All set? Great. So, how's everybody doing this afternoon? Good? Good conference so far? Excellent. Okay, so today we're going to talk about Microsoft Cognitive Services. So if you're in the wrong room, now's the time to leave. Everybody doing okay after lunch? Staying awake? Unfortunately, I don't have any sugar, so hopefully if you're feeling like the folks in the photo here, we can keep you awake for the next hour or so. Sales pitch. New York City Code Camp is coming up on October 20th. There's still room, so if you'd like to register, go to codecampnyc.org. It will be Saturday, October 20th. This talk won't be there, but there'll be lots of other great content. So if you're in the mood, come see us towards the end of October. Before we get into this talk, just a little bit about who I am, and more importantly, I suppose, why you should care to listen to me. My name is Steve Bohlen. I read books and write software for a living. This is as opposed to the alternative career of reading software and writing books for a living, which lots of people do to great reward. But for myself, I'm really a practitioner of software engineering rather than an author about it. So most of my experience comes from real-world experience and real-world examples. I blog, I record screencasts, I speak at events like this so I can share what I know with others, but also so that I can learn from you. So as we go through this, session here today, if you have questions, comments, and so on, feel free to shout them out. I'll see if I can answer them. If we have time, great. Otherwise, I'll be out in the hallway afterwards and we can pick up where we left off. This slide I'm not going to bother with, but essentially it's there for anyone who bothers to download the slide deck after the fact. It basically says that I've been writing software in a lot of different languages over the past 25 years. I'm currently a principal software engineer at Microsoft, former MVP. I run a couple of user groups, and as I mentioned, also the New York City Code Camp. Former MVP, all the rest of that nonsense. There's also information there about how to contact me. So before we get too far into this, I am a Microsoft employee, but these thoughts are entirely my own. Right? So what this really means is it's fine for you to leave this conference and say things like, that guy Steve from Microsoft said, but it's not okay for you to leave the conference and say, Microsoft said, right? It's a subtle distinction, but it's important, okay? As I said before, if you have questions, feel free to ask them as we go through the content. Let's talk about what is machine learning, right? So the formal definition of machine learning looks like this. A computer program is said to learn from experience E with respect to some class of tasks T and performance measures P, if performance at tasks in T is measured by P, improves experience E, which is an interesting sort of computer science-y definition of machine learning. But if you tear it apart for a minute, what you'll actually realize is it's not really about machine learning. It's about any learning, right? What it basically says is if you get better at something with experience, then you're learning, which I suppose is a decent definition of learning, but it doesn't really help us when we think about machine learning. So when we think about machine learning, I like to sort of phrase it this way, right? It's computational learning using algorithms to learn from and make predictions on data, right? So as distinct from just generalized learning. So how many people in this room have heard of machine learning? Okay, nearly all of you, right? So why is that? Well, let's talk about why that is. So who in this room has seen this chart prior? Great, some of you, right? Anybody know where this came from? What is this chart for somebody who raised their hand? Anybody? Right, so it is from Gartner, right? So this is the Gartner Technology Adoption Cycle graph, right? From Gartner, the guys who make the Magic Quadrant and all kinds of other wonderful white papers that you have to pay to buy, right? A couple of things that are interesting about this chart. First of all, Gartner is a very data-driven company, right? When they do their Magic Quadrant and so on, they do so by going out in the world and doing all kinds of surveys and analysis of data and so on and so forth. And so one would be inclined to think that this chart is actually also based on data. One would be inclined to think that a bunch of really smart people from Gartner got into a room and said, you know what, we've noticed this recurring pattern with technology adoption. It starts down in the bottom with some kind of trigger, right? And that trigger can be any number of things, right? It could be the invention of the microprocessor. It could be the microprocessor becoming 40% more power efficient. It doesn't really matter what the trigger is, but it's something that changes with technology. And then pretty quickly we get to what they call the peak of inflated expectations, where everybody thinks whatever the new technology is going to save the universe and solve world hunger and make everything roses and unicorns and we're all going to be happy. But then what typically happens is we enter what they call the trough of disillusionment, where we sort of go down from our excitement about the technology as we start to discover all the things that technology is not nearly anywhere near as good at as it had been pitched for, right? And then we end up in what Gartner calls the trough of disillusionment. Now, what's supposed to happen is that over time, we will sort of climb our way out of that trough of disillusionment. The idea is that, okay, the hype is over, but now we've learned what the technology is good for and what the technology isn't good for. So we start to develop patterns for utilization, where it can help, where it's not, where it's appropriate, where it's not. And then eventually we reach what Gartner likes to refer to as the plateau of productivity, where there's enough use cases where people understand enough about the pros and cons of the technology to apply it properly and effectively. As I said before, an interesting thing about this chart is that it actually is not based on data. There's actually no empirical study that suggests that any technology adoption actually follows this pattern. It's entirely intuitive, right? You look at this graph and you say, yeah, that sounds about right, right? But the truth of the matter is, despite Gartner's reputation for data-driven everything, this particular chart is not at all based on data. But I do think that because it is intuitive, we can all sort of look at it and say, yeah, that feels about right, right? And so part of the reason most of you raised your hands when I said, who's heard of machine learning, right, is that machine learning is kind of right here right now. Right? The peak of inflated expectations. Everybody's talking about it. Everybody wants to know what to do with it. Nobody really quite knows how to take advantage of it and make use of it and all the rest of that, right? The other thing that's interesting about this chart is that this actually only shows one potential path through technology adoption, right? It's certainly not a given that after the trough of disillusionment, there will actually ever be a slope of enlightenment, right? In fact, all too often, technologies follow this path, where we get into the trough of disillusionment and no one ever figures out the technology is good for anything, right? And so it's important to pay attention to the fact that this is another potential path through this diagram, right? Even though it's true there's always a trigger, and it's probably true that, certainly given the trade press, there's also always inflated expectations, it's not a given that we're ever going to figure out what the technology is really good for and be able to leverage. Just bear that in mind, right? So, when we speak specifically about machine learning, what's important to understand is that this is not its first bite at the apple in terms of going through the Gartner technology adoption chart, right? The truth is that machine learning and artificial intelligence has had multiples of these working back through time, right? And whether there's 5 or 6 or 4 or 3 of them is sort of debatable, but the truth of the matter is we've been through this cycle many, many times with machine learning. This is not our first shot at this as an industry, right, or as a planet for that matter. And so, especially given the fact that there's no guarantee we'll ever get up that slope, right? What's happened in the past is we've never gotten up the slope of enlightenment. In fact, we've kind of maybe improved a little bit, which is sort of what this diagram's trying to show, is that we didn't sort of continue to slope into nothingness, but we just kind of happened along a little bit, and then there was something else, right? And it didn't matter what the something else was, but the something else was suddenly something that made machine learning better, faster, stronger, more approachable, whatever it might be, right? Some new trigger that made everybody say, okay, now let's do the peak of expectations again for machine learning. So we've been at this a number of times. And the reason this is important to think through is you always want to be asking yourself, when you're faced with a technology where you look at it and you say, I really think there's value in this technology, right? I think by looking back at previous attempts to implement that technology and take advantage of it, you can learn a lot about what went wrong and apply that to how we might make sure that we do find a slope of enlightenment in this latest adoption cycle. So, one more show of hands. Who thinks they have a problem that machine learning can help them with? Some of us? Interesting. Okay, so not as much of the audience as I would have thought, but that's okay, right? Part of the reason that typically we get a lot of hands for that, though, is that machine learning is just about everywhere, or can be just about everywhere, and can be applied to just about any class of problem. This diagram is just sort of a goofy architecture picture. It doesn't really mean anything per se, but you can tell by some of the various graphics that we've got everything from World Wide Web to shopping to email to education and so on and so forth. All of these things are potential applications for learning. And because machine learning is one of those technologies where it's not like a web framework where there's literally just one thing you can do with it, right? If you're not building a website, there's sort of no point for you to learn a web framework. But if you're doing just about anything where your computer has to make decisions based on data, and let's face it, that's pretty much the definition of virtually every piece of software anyone ever writes, is a piece of software trying to make decisions about data, right? Then you've got a potential application for machine learning. So here is an XKCD slide. Our software development product manager comes up and says, when a user takes a photo, the app should check whether they're in a national park. And our developer, she says, sure, I can do a GIS lookup. It'll take me a couple of hours, right? Then the product manager says, well, actually, it also needs to check whether the photo is of a bird, right? And now our developer has to respond with, I'll need a research team in 5 years, right? And the moral of this story, right, is it can be hard to explain the difference between the easy and the virtually impossible. Because in a sense, these are really just two questions a computer has to ask, right? Am I in a national park, and is there a bird in the photo? But one question is notably easier than the other one to answer, right? So we can imagine having this conversation. What's interesting to think about, and this is important certainly in the context of Microsoft Cognitive Services, is why is it that the first answer to let's see if we're in a national park is actually so easy, right? Is it because the developer is a geospatial mapping expert? Is it because the developer has written a huge piece of software with every map of every landmass and every national park on the earth right on their own server under their own roof? Of course, the answer is no, right? What the developer's really saying is, I'm going to use a GIS lookup service. I'm going to go to something on the internet that knows the answer to the question I need the answer to, and I'm going to have my software ask that question, get the answer back, right? And so the reason it's easy is not because the software developer is a GIS expert, but because there's a service on the internet that makes answering that question pretty much old hat, right? Now, the reason that we might need a research team in 5 years is because from the developer's perspective, there actually isn't a service on the internet that answers the question, is there a bird in the photo, right? And if there was, keep this in your head, if there was, this might also just take the same couple hours, or maybe even 5 minutes. I'm not advancing the slide any longer. Let's try again. Okay, so why do we need 5 years and a research team? Well, imagine you want to do machine learning. How do you do machine? Well, you might start here. You could learn some linear algebra. You might learn probability theory. You might need to learn some calculus because linear algebra is insufficient on its face for much of what you'll need to do. Once you're crunching formulas, you need to sort of understand statistics so you don't make the wrong choices with the formulas you're applying. Simple statistics are insufficient, so you might need multivariate statistics. Understanding what those statistics tell you mean you actually need to learn some information theory. And after you've amassed all of that mathematical skill and knowledge, you are finally ready to learn about machine learning. That's a hell of a lot of prerequisite, right? So let's imagine you've got the prerequisites. Now it's time to learn about algorithms. Here is one possible way to classify a number of different machine learning algorithms that you might choose to apply to one or more particular problems you're facing, right? And this is by no means, by the way, the only way to categorize these and organize these. This is just one way to think about a taxonomy for algorithms in machine learning. So in this particular context, we've broken them up broadly into supervised and unsupervised. But even once you decide which of those you need, and by the way, understanding the pros and cons of which choice to make, right? You then need to figure out, what am I doing? Am I doing classification or regression or clustering? And once I decide what kind of problem I'm trying to solve, which algorithm within those categories is really going to solve the problem for me, right? And so even after you've mastered all of the statistics and the math and the calculus and all the rest of it, now comes the real machine learning part of this problem. Now, the clever among you will actually notice that there is some commonality in this diagram, right? Down here at the bottom, we've got artificial neural networks turn out to show up everywhere. So, hey, I got an idea. What if we just solve the problem by doing artificial neural networks always? Right? That would be one way to solve this problem. At least this diagram implies that, certainly, right? The truth is, yeah, that might work, actually. But there are certainly any number of problems with artificial neural networks, not the least of which is that they take a long time to train properly. But let's understand the difference between supervised learning and reinforcement learning. Supervised learning is kind of what you think of, right? If I sat down with you and said, I'm going to help you do your math homework, supervised learning would be, as I watch you working through the math problem, I would make suggestions. I could say, no, don't carry the 1 there, you know, divide by 12 over here, right? That's supervised learning. I'm going to help guide you to the answer, and over time, you're going to get better at getting the answer yourself. Reinforcement learning, if I wanted to use reinforcement learning on your math homework, reinforcement learning would be me going to you and saying, finish as much of your math homework as you can in the best way possible, and then come and show me how much of your math homework you were able to get done. Now, in the reinforcement learning scenario, you could actually solve this problem by breaking into the school, photocopying the math exam, and writing down the answers to the homework and giving me the completed homework assignment, right? That counts in reinforcement learning. Right? Reinforcement learning is all about the outcome. I don't care how you achieve the goal, I just want the goal. And the closer you come to the goal, the more reinforcement I'm going to get. A lot of machine learning boils down to things like classification and regression, right? Classification, as you can see in the diagram on the left, is basically this notion that some things are similar and some things are different. And machines are pretty good at determining like characteristics and unlike characteristics. Regression is the notion that data follows a pattern, and if we can look at patterns in historical data, then we can project those patterns forward into new data, right? And most machine learning tends to break down into a couple of these kinds of categories. However, even these are fraught with some problems, right? In this particular case, not everything actually has a clear regression structure to it, right? Data may well be scattered much like this, and as, again, actually, interestingly enough, another XKCD slide, right, actually shows that in this particular case, it's easier to draw a constellation than it is the mathematical regression through the data. Not all clustering is necessarily obvious in terms of how you cluster it, and the math you use to describe clustering algorithms is sort of non-trivial. On the left-hand side, if you've got data that manages to be easily classified according to linear algorithms like this, that's pretty easy. On the right-hand side, we start to get a little complexity. Obviously, the math required to describe that line on the left versus the math required to describe the sort of asymmetrical ellipse on the right-hand side is much more complicated math, but these get worse, right? So we also have to deal with discontinuous clustering. What if not all the things are actually all in one bunch, but they're in multiple bunches scattered around, and so on and so forth, right? And then we have to worry about math that gets much more complicated because of dimensionality. In this particular case, this is a graph of engine horsepower, miles per gallon, and vehicle weight, right? Now that's 3 particular vectors of dimension. Imagine a problem that's got a 4th, 5th, or 6th. All of a sudden, you can't draw it anymore because as humans, we've actually gotten pretty good at representing 3 dimensions and 2 dimensions. That's what we see here. We're actually terrible at 4 dimensions, or 5 dimensions, or 15 dimensions. We don't have ways of visualizing them. We have ways of describing them mathematically, but they become really, really complicated for you to actually describe in formula. And so as the problem gets more complicated and the solution and the data you're analyzing becomes more complicated, it becomes increasingly challenging for you to visualize it. Which leads to stuff like this, right? Now, probably like most of you in the room, I had some calculus in college. Probably also like most of you in the room, I have not used much of that calculus since college. And fortunately, I suppose for many of you in the room, the distance between my using calculus in college and you having used calculus in college is perhaps a little shorter. But nonetheless, I'll bet you've forgotten pretty much all of it, just like I've forgotten pretty much all of it. So when someone says to me, yeah, I've solved it, I just kind of have to take it on faith that they have, right? Or crack open and dust off my book and figure it out, right? This guy in this photo is immensely proud of his blackboard. And in fairness, if I knew there weren't any errors up there, I would probably be pretty damn proud of my blackboard too if I had actually come up with it. Right? But the reality is that as software developers, we're really not paid to fill blackboards full of formula. We're paid to write software that solves problems. So if a prerequisite to writing software that solves problems in a creative and valuable and interesting way is filling a blackboard full of formula like that, a lot of us are going to be knocked out of the box immediately. It's just not going to be possible. So what if instead of writing the formula, we just turn the system loose on the data and say, here, learn, right? Machine, learn like a human. And this is the notion of neural nets. We talked earlier when we were looking at algorithmic classifications, there was neural networks happened to be common across all of those as a potential solution. And that's because neural nets are essentially learning turned loose on machines, right? They are almost always reinforcement learning, where you give them a goal and an objective, and you don't really care, and this is actually important too, you'll never know how it arrived at the result, right? In my hypothetical of the math homework, for example, the system might return to me a 100% completed math homework, but I'm actually never going to know if it accomplished it by actually working the problem or by breaking into the school and stealing the answers, right? Or by social engineering and stealing the email password from the teacher and all the rest of this, right? I'm just going to know that it got the answer. Now, if all I care about is the answer, and I don't really care about how valid that answer is or understanding how it arrived at the answer, then this actually might be an entirely legitimate way to solve the problem. However, in a lot of cases, we find that we don't just care about getting the answer, we care about how and why. Because one of the big important things to think about is reproducibility, right? When you don't know how something learned, and if the act of doing something and making a decision makes something smarter, it means it's going to make the decision a second time ever so slightly different than it just did it the prior time, then not only are you never going to know, but you're never going to know whether it's getting any better, right? So traceability with these things becomes a real challenge and a real problem. And so saying to the machine, just kind of abstractly learn, isn't really an answer for us either. However, we are still faced with a very real problem, which is that, as I said earlier in the talk, lots of us have problems for which machine learning is probably an applicable, valuable ingredient, even if you're not thinking it is. Your hands didn't go up when I asked the question. The truth is that if you look at this diagram, we've got sort of machine learning in the middle, and then we've kind of, again, broken it up into supervised and unsupervised and reinforcement. But you can see when you look at the nodes around the ultimate extreme leaf nodes of this diagram, what you see are things like customer retention. Who's dealing with customers and does not care about customer retention? Right? No hands, because everybody does, right? Now, you may not be in a business that deals with customers, you may be in a business that deals with predicting population growth or targeting marketing or whatever it might be, right? But the point is that almost nobody is in a business that isn't doing at least one or more of these things. And at least every one of these on this diagram and lots of other use cases are scenarios that could benefit from machine learning. That's why even if you don't think you have a problem that can benefit, turns out if you think it through, you actually almost certainly do. Now, whether you can do effective machine learning, caliber and scope and scale of the data you have is a separate question. But whether you have a problem for which machine learning is probably an ingredient, are debate in most cases. So, how do we actually make this work? This brings up a talk about how Microsoft thinks about artificial intelligence. We think about so this is not how we think about artificial intelligence, right? It could be, right? It certainly could be. And we do have tools, by the way, that will help you build machine learning algorithms. But this is actually not a talk about those. So we think of AI in a number of different buckets. There's sort of agent-based AI, things like Cortana and so on. There are applications that leverage AI. There are services that offer AI capabilities. And then there's infrastructure in which you can run your own machine learning algorithms and so on. We're going to focus today on services, and specifically we're going to focus on cognitive services, but it's worth understanding that these cognitive services we're going to talk about don't exist in a vacuum. They exist in a continuum of a number of other capabilities that we offer in the AI/ML space. So at Microsoft, our cognitive services are broken up into categories based on the type of data they interact with. Things like vision are for things like video, imagery, and so on. Speech, actual vocalizations and so on. Things like text-to-speech and accent detection and these sorts of things come from the speech AI. Language, right? Actual diagramming and deconstructing of sentence structure, understanding entities are in the knowledge space. Search, we've got lots of AI that deals with search. And then we have things that are in labs, which are those things that are very much works in progress and experimental, which you're encouraged to experiment with, but may or may not necessarily ever see the light of day. If we look at what some of these things are, so in the vision category, we've got things like computer vision, which does object detection and these sorts of things. Content moderator, which is able to do things like detect nudity in photos, kinds of things. And a number of other things. Emotion, obviously, is going to be able to detect emotion. Face will do facial recognition. We've got video and a number of other things, of course. In the speech area, what we've got are things like the speech generation, speech recognition, and the custom speech service. In language, we have all kinds of things like linguistic analysis, where the translator lives, and text analytics, and those sorts of things. In the knowledge space, we have a pretty significant knowledge graph. A lot of these same technologies, so it's worth understanding the way we think about the cognitive services is a lot of these same capabilities are the engines that have been driving various interactions with products within Microsoft's larger product ecosystem for a very long time. We've taken those learnings from those and actually turned them outward and made them available as capability to you, right? So if you're anybody familiar with the real-time speech translation experience in Skype, where I can be speaking French and the person on the other end of the line is speaking Italian, for example, right? If you've ever used that capability, the way that actually works is through the exact same technology that powers a lot of these cognitive services. When I speak Spanish, for example, that Spanish is being captured in text through the speech-to-text engine. It's being translated to Italian text using the translation engine. It's being vocalized to the Italian speaker on the other end using the text-to-speech engine. And that's how I can speak Spanish and that person can hear Italian on the other end and vice versa. The real point there is that you could build that experience today using these exact same services, right? Because they're the same capabilities that power a lot of the Microsoft products. In the case of search, it will surprise no one that most of our search capabilities are Bing enabled. Many of them are using Bing on the back end and data from Bing on the back end in order to be available. And then in the labs category, excuse me, we have a number of these that are, as I said before, very much experimental, very much exploratory. You're free and welcome to use them, but they may or may not necessarily be proven viable enough to actually see their way to an actual service. So why would you think about cognitive services? Well, this kind of gets back to the way, one of the ways we at Microsoft think carefully about why that trough of disillusionment wasn't previously dug out from, right? One of the reasons is, as I was showing earlier, the sheer amount of math skill required to do machine learning is overwhelming for most developers. It's also not really required, right? So one of the things that we're doing with the cognitive services in terms of making sure that this time around the ML experience does get to a plateau of productivity is by taking the complex stuff and putting it behind a service facade and allowing people to consume the capability in the same way you might consume that GIS service from our original XKCD cartoon, right? So why would you use the cognitive services? Well, the first one is they're very easy to use, right? They all have REST APIs. So raise your hand if you are writing software in a language that can make a REST call. Congratulations, you just met the minimum bar for being able to use cognitive services, right? And today, of course, everyone can. They are flexible because they're REST APIs, and as I said before, you can call REST from just about anywhere. You're going to make the same API call, whether it's your website making the call, whether it's your mobile app making the call, whether it's your server under your own roof making the call, it doesn't matter, right? And tested, as I mentioned before, a lot of these are the same algorithms that power a lot of our own internal capabilities. When we're looking at, in a minute, we'll do a demo of some of the computer vision API. That is the same API and the same capability and the same learning that actually goes into Bing image classification. So when you do a Bing image search, the algorithm that's actually picking through the images to find an image that matches your search criteria is the same algorithm that goes into analyzing your own image when you die, for example. So the other way to think about this is these algorithms are getting, and services are getting smarter all the time. Why? Because I don't actually know exactly how many new images Bing image search indexes every day, but every day it does, it learns and gets better at indexing images, right? So what's a typical interaction paradigm for a cognitive service look like? Well, it's a REST call, right? So first you're going to set a request header. Typically this is where you're going to provide an API key, right? Where you're going to identify yourself as being authorized to call the particular API and that usage of the service is going to be tied to your own subscription. You're going to compose a request. This request can be a combination of things. It can all be in the query string. Potentially a lot of these are JSON body payloads. Plenty of them have content bytes, right? So you might very well byte encode a photograph and send it to the API, right? Or you might have a video you want analyzed, and the video, of course, is way too big to byte encode and put in a post, right? So what you'll do is you'll send a URL to the video, right? And the service itself will navigate and traverse that URL in order to analyze the video, for example. You're going to make your HTTP call. These are almost always posts. Sometimes they're gets, but they're almost always posts. And then you're going to get back a simple JSON response, right? The content of this JSON response is going to be the results of having analyzed and performed the operation on the payload that you actually sent to the post. So the interaction paradigm for these is actually very simple and forward. Let's talk about the life cycle of one of these, just so we can kind of understand the difference. So I mentioned labs, right? It's important to understand sort of the different SLA guarantees on these things. So labs are entirely experimental. There is no SLA. The service might be up, the service might be down, and there's no guarantee that it'll ever get out of lab. We may actually release a lab offering and allow you guys to bang on it for a while and discover that it's actually so miserably poor, either from a quality perspective or even from a performance perspective, that there's just no way we can productize this thing, so it goes away. But a lot of the lab stuff will actually move to the next phase in the pipeline, which is preview. In the preview phase, there's still no SLA, so the service might be up, the service might be down. The API is mostly fixed and mostly stable by this point, but there may be some breaking changes that happen now and again. There is no SLA, and again, these are expected to move to GA, but there's still no guarantee. We might actually still pull something in preview for a lot of the same reasons we pull something in lab. And then lastly, things get to GA where the API is stable and fixed and versioned, so if there's a breaking change, the API version will change. There is now an SLA for these things, and there's formal support. So if something is wrong with it, you can call Microsoft, and we will actually help part of our normal support channel. It's worth mentioning just briefly the Cognitive Toolkit, because I do keep talking about neural networks. So CNTK, the Microsoft Cognitive Toolkit, is our implementation of neural nets. So if you have a problem where you do actually need more generalized machine learning, then CNTK is worth being aware of, at least as in existence. But what we're actually going to do is we're going to focus in on the cognitive services first. So let's take a look at some of those in action. So here I am at our web page, and it's really easy to get here, even though it's got a tremendously long URL. It's basically just azure.com/cognitive, which will redirect to here. So for every one of the cognitive services, remember I was mentioning that they are all categorized into the types of data that they operate on. Here they are: vision, speech, knowledge, and so on. For almost every one of the services, there is a way for you to interact with the service and experiment with it without writing a single line of code. You can do so entirely from the web portal, and that's what we're going to do just now. The reason for this is that even though it's obviously trivial for you to write a little snippet of code that makes a REST call, right? Anybody can do that in about 5 minutes. Free if you're doing it. But the point is that anybody can do that, but you shouldn't have to. So if you've got a sample image that you need to analyze and you want to know, is this service capable of giving me any kind of the right answer, then you can experiment with it directly from the website without having to write a single piece of code or open your IDE. So let's actually take a look at that. So let's go to Vision. And within Vision, you'll notice that we've kind of categorized these things into different buckets. We've got computer vision, we've got face, we've got the video indexer, we've got the content moderator, and so on. I'm actually going to start out with let's do face. So here's a web page that allows me to see the face API in action. Remember I said before, what you're getting back is just a JSON payload that's the result of the analysis, right? So to give you a sense as to sort of the caliber and quantity of data that's available, here is some sample JSON that's actually returned here, right? What you can see is that you're getting the coordinates of the rectangle, the bounding box where the face was actually detected in the image. But you're also getting a number of additional pieces of information that aren't just, hey, yes, this was a face, but you can see, for example, there's a 99% confidence that the hair color was brown and a 57% confidence that the hair color was black, right? This is really important for machine learning. And machine learning, remember, you never actually ask a question and get an answer. You always ask a question and get an answer with a confidence factor. Now, depending on your use case for that answer, the confidence factor can be high enough for your needs or not high enough for your needs, right? Simple example is if I want to try and identify how many people are in this room using computer vision, it doesn't really matter if I'm 100% sure that, you know, your hair is blonde and your hair is black and all the rest of that. But it does matter that I can tell that you're two different people. Right? So different confidence for different factors based on what you need for your particular use case. And if you scroll down to the rest of this, you can actually see all kinds of other things, right? So you can see, because it's got the bounding box for the face, it can do things like detect the face's orientation to the camera. It's got a pitch and a roll and a yaw, right? These are actual offsets for the orientation of the face and so on. You can see that in this particular case, reading glasses is true, and we've detected eye makeup is true and lip makeup is true. So there's a fair amount of data that comes back from this, just by saying, here's an image, send it to the Face API, give me the JSON back. Right? Now, you may not need all of these answers, right? But the point is that this is a sense of the richness that you actually get. And you'll also notice that even just through some of the sample images, like if we pick this guy, what you can see is that we'll see here that even though he's wearing a hat, right? It doesn't say, I can't see any hair, so I'm assuming you're bald. It's actually detected he's wearing a hat, and that underneath the hat, he's actually got hair. So what we see here is that he's not bald, that's 0.0%, we're sure he's not bald, but the hair invisible is true, because he is in fact wearing a hat, right? Now, you can also experiment, as I said before, with some of your own photos. So I'm gonna pick myself, just so nobody gets insulted, right? And I'm gonna say, there we go, right? Now, in this particular case, thanks to machine learning, it's 82% sure that I'm bald. Fortunately, however, it is pretty sure I'm male, so I guess we got that part, right? And it's actually pretty good on age, too, as it turns out. But the point is, right, that you can experiment with this. So if you said, is the Face API going to help me in building my software? Take a sample image that you think you're going to want to analyze and just interact with it on the website. Real simple, right? Don't even have to write the REST call. Don't have to provision a service, get an API key, do anything fancy like that. Just experiment right on the website. Most of these have similar kinds of experiment on the website APIs. You can also put an image URL in there, for example, and go grab something off the internet. Fine, right? If we look, for example, at emotion recognition, right? Here's an example of the emotion API coming out of this. So here, we've looked at this face, which, you know, remind ourselves looks like this, right? So we've got the bounding box for the rectangle, but we've also got values for all the different emotions we can detect, right? And so pretty strong on anger, pretty weak on contempt, pretty weak on disgust, pretty low on fear, reasonable on happiness, pretty high on sadness, and very high on surprise. Right? So these are all graphed between 0 and 1, where 1 is the most surprise one could evidence, 0 is no surprise. So it doesn't just say, you look angry, I'm 82% sure you're angry. Right? It says, these are all the emotions I detected, and this is the strength of the emotion in the photo. So if you're a combination of angry and sad, we could probably detect that, right, within reason. Again, just as an example. So if we go back and look now at computer vision, just briefly. Here is a sample image. And what you can see if you look at the tags, right, is having analyzed this image, we've got train, platform, station, building, indoor, subway, and for each one of the tags in the JSON down below, you can see the confidence, right? So we're 99% confident that there's a train in this photo. We are 99% confident there's a platform. We're 97% confident it's a station. So remember I said earlier, right, a lot of this technology is the stuff we use internally. When Bing indexes this image, this is the same way when you go to Bing image search and type in train platform. Right? We won't give you ones where platform is lower than, whatever percentage we've agreed is valid, right? In fact, if you go to Bing image search and actually say train platform as your search criteria, the order in which those search results are actually ranked for you is in confidence based on whether we thought there was a train platform there, right? So the 1.0, if you ever got there, right, or 0.99999 train platform is at the top of your search results, and on page 3,000,005, is the one where we've got 0.000002 confidence train platform, right? The truth is we cut it off after a point. Okay? It's obviously not a train platform. But my point being, right, there's a scenario where we are using the confidence factor to rank results, right? And have the software behave based on what level of confidence we have in that stuff, right? So the other thing I'm going to look at here, just to give you a sense as to how this works, is this is a piece of software that you can actually take a look at yourself. It is a Windows 10 app. It is on GitHub. If you go search GitHub for Intelligent Kiosk under Microsoft, you'll find the source code for it. It's called the intelligent kiosk because it basically wires itself up to a number of cognitive services and provides some real-world use cases for understanding how these work. And because it's in GitHub, you can look at the source code and understand how to write them all. I will tell you in advance that there's nothing magic about the content in the GitHub repo because, again, they're all REST calls. All it's really doing is showing various ways that you can interpret the JSON results back in order to do interesting things in your software. So as a simple example, let's take a look at something like the Face API Explorer. So this is me, and what I'm going to do is I'm going to scoot in to get my face a little larger. I apologize, you're going to have to stare at me. I'm going to take a photo, and it's doing a couple of things here, right? So it's 61% sure that I'm Steve Bohlen, but importantly, it has drawn some of the geometry markers for where it's detected my particular facial aspects and elements, right? So my mouth, my eyes, the outline of my nose. If I do something like this, right, what we'll see is, you notice how the geometry around my mouth has changed, right? Because it's detected where my lips are, but it's also detected that the geometric shape of my open mouth is different than it was in the prior photo. These are the kinds of input that go into things like the emotion API and so on, right? My mouth closed, or the corners of my mouth up. Am I happy? Am I frowning, right? What you can also see with this is that there are limits to this. So for example, as I turn my head, there's a point at which so even at 3/4 profile, it can actually still detect the geometry, right? Now, it can't really see my left eye in this photo because it's slightly behind my nose bridge and slightly away from the camera mode, right? But it knows what a human face looks like, and so it knows I can see some of your eye, and I can interpolate where the rest of that is, right? And so even though I'm not necessarily square onto the camera, it's still able to do a fairly decent impersonation of detecting my facial location. There is a point at which I can turn too far away, by the way, right? And now you notice it didn't give an error, right? But it also didn't draw any geometry on me. It can't tell where I am, right? Because it's no good at profiles. So why does it know it's me? Well, it knows it's me because I've taken some time to train it. So I've given it 2 photos of me, which is why it's only about 60% sure that it's me. If I gave it 4 and 5 and 12 and 16 photos of myself in different light, with different head orientations, with different emotions, wearing different clothing, with different backdrops and so on, and said, all of these are Steve, that confidence factor would go up, right? So it's a matter of how much I can train it. And because with this particular application, you can actually experiment with that, it's possible for you to determine how much data is necessary in order to train the Face API in this simple example to be accurate enough for your particular use case, right? So you can experiment with the API this way as well. And by the way, right, what's actually happening there is the application is making the call to the API, getting the JSON back, and then using the geometry in the JSON to actually draw the dots on the screen, right? The red dots, the green dots, the white dots, and so on. That's actually data from the service. Almost no processing is occurring locally here. All that's happening locally is the JSON is being interpreted and drawing little dots superimposed on the video image. The thought work, so to speak, is being done in the cloud. So let's also look at one more. So this is the emotion API. It's pretty sure I'm happy. I'm not terribly angry and I'm not terribly contemptuous, at least not in this image. Now I'm kind of angry and disgusted at the same time. I'm more angry than disgusted, but apparently I'm both of those things. And then lastly, right, now I'm surprised and maybe slightly angry, but mostly surprised. And again, what's happening here, right, is the system is returning the JSON, and the application is merely parsing that JSON and using that to know how to draw the little speech bubble that tells me what's going on. Now, this is interesting for Face and so on, but it's important to understand that we have a lot of APIs that deal with other data types as well. So here, for example, is the Bing News Analytics app. And what this actually does is relies on the sentiment analysis API. What the sentiment analysis API does is it allows you to send text to the service, and the service will detect the sentiment, positive, negative, and so on, in that text element. So, for example, here, I'm going to say to Brett Kavanaugh. And then what's happening here is the system is actually doing a Bing search for all of the articles that have been posted on the web that happen to have that term. And then is taking, in this particular case, the headline rather than the body of the article, and that was just done for speed and performance reasons. You could actually send the entire body of the article if you're great for that. We're just taking the headline because it's quicker. And then we're actually scoring these as to whether the sentiment is positive, neutral, or negative. And again, sentiment comes back as 1 being wholly positive and 0 being wholly negative. And even what we decide for the sake of the application as being neutral is totally up to us on the application programmer's side. In this particular case, I think we said like, you know, positive 30 and negative 30, and then the middle 40 is neutral. But you can see the green stuff is positive, the brown stuff in the middle is somewhat neutral, and then down at the bottom, presumably we'll get some negative articles as well, kind of a thing. You can imagine doing this with search terms on and of course the graph on the side is being drawn there to demonstrate how you can actually look at the aggregate data. And what's happening here, right, is you can imagine building an application that looks for search terms that are based on you know, positive and negative marketing sentiment for your product, for example, and these kinds of things. It doesn't need to be Bing as articles, right? This is just an example of one set of data sources. What if you took your entire database of customer service reviews or customer service tickets or Twitter feed for your product or company, and so on and so forth, and did sentiment analysis on that, right? You could easily see whether trending was going positive or negative. And again, interestingly enough, right, you can actually also go back and in the context of the website, you can actually experiment with this yourself. So if you go to something like, I think it's language. Yeah, and do sentiment analysis, right? So here, again, we can actually interact with the web page in order to get a sense for how the API actually works. So I had a wonderful trip to Seattle. I enjoyed seeing the Space Needle. And what you can see here is it's identified some key phrases. It's identified a very positive sentiment. It's pretty confident that it's English. And then it's identified what we call linked entities, right? So this is not just detecting terms, but actually logical entities behind which there's actually knowledge and information. So I could say, for example, this was the worst conference I've at. Food sucked. And we'll say analyze. Right now, what's happened is, right, it's still confident it's English, but you'll notice the sentiment went down from 98% all the way down to 4%, right? Very, very negative. That's basically all I said. But you could imagine like a review of your product that was some combination of positive and negative, right? We'll be able to determine, is it totally, you know, is it on net positive? Is it on net negative? Right? And if you look at the JSON that's returned, for example, you can see things like detected language. You can also see here key phrases. Whoops, sorry. You can also see here key phrases like worst conference and food and these kinds of things. So if you're wondering not just, hey, this was a negative review of my product or my company or my service or whatever it might be, but what were the parts of the thing they were not liking, right? So if I were TechBash and I saw this as posted to the website or something, I'd say, oh, okay, so they didn't like the conference and there was definitely something about food. If I want to improve the food, I could definitely go look at what this person said and actually make some judgment calls about what we might do for next year. So one last API we're going to take a look at because it plays into the story, and that is the Vision API Explorer. So what I'm going to do is I'm going to go out on the World Wide Web, and I'm going to say birds. And all this is just going to do in the app, of course, is just search for photos of birds, right? And what I'm going to do now is I'm going to grab one, and what we're going to see, right, is that it's 97% sure it's sitting, 97% sure it's outdoor, 92% sure it's an animal, 82% sure it's orange, 70% sure it's a bird. So remember our scenario, right? Is the photo in a national park? We'll ask the GIS service. Is the photo of a bird? We'll just ask the vision service. The same REST call you make to figure out whether the GPS coordinates are in a park. It's literally that simple, right? And so And by the way, right, 70% bird might actually not be good enough for you, right? The answer to your scenario might be, sorry, that's not enough of a bird for it to count, right? In which case you might find yourself needing to wait until you get a more certain answer, like, hey, I think you're in a park, but I'm not sure you have a bird. Why don't you keep going until you get a little more sure? Here we're 100% sure it's a photo of a bird, right? And you can imagine that making sense because the prior photo was a bird in a tree with a lot of other leaves, and the bird wasn't necessarily obviously the focal point of the photo. Here the bird is much more dominant, and see that the bird in the photo is equally enhanced. So, finish this up. The point, right, as I said before, is that the reason it's easy to do the GIS lookup is because there's a service. The reason it's easy to answer the question about the bird is also because it's a service. So the point is, instead of things like this needing 5 years in a research team, we can get rid of all of this and solve a lot of the machine learning usage scenarios in exactly the same way we solve a lot of other complicated scenarios. Let somebody with the geospatial expertise build the GIS database that can answer the question, is this latitude and longitude in an park? Let somebody with the expertise at machine learning algorithms write the code that actually detects whether there's a bird in the photo. You get to just use the service, benefit from the result. That's the end. So are there any questions? What time are we done? 3? 3:10. We got 10 minutes. Yes? So, yep, so that's a good question. So the question was, is the JSON return from the services designed to be stored in a NoSQL data store or something along those lines? The purpose of the ID is actually not for that, right? And what I usually recommend to people is if you have a need to persist the result, I would wrap the result in some other data structure that you then persist that meets the needs of your persistence store, right? So part of the reason for the ID for face, for example, is I didn't show it, but you can experiment with it on the website. But there's a portion of the face API that does face comparison, right? And so each face that it detects gets a unique ID. So if it detects like 2 photos of me, would both get the same ID because it would say the face ID is the same. I don't know that it's Steve necessarily, but I know that this photo represents person A and this photo also represents person A. In this case, A is that ID. And so if you give it a 3rd photo or a 4th, 5th, and 6th photo, it can figure out, oh look, this one is also person A, but these 2 photos are person B and C I haven't seen before. And so part of what the API is doing is giving a unique identifier for that face. And that's the way it works similarly with a lot of the other services as well. So the ID is definitely not there with the intent that you'll use that as sort of your, your primary key or your retrieval index for a NoSQL. Yes? Yep. So one of the things we didn't look at, and I will show you now, just because we can, is every one of these pages for every one of these services has a nice documentation link. When you go to it, you can actually see everything from, this happens to be text analytics, right? What is text analytics, quick starts, tutorials, how-to guides. There's a full-on reference, text analytics API reference if we wait for it to load, right? Here is, literally the whole ball of wax documented down to every property returned, what it means, and all the rest of that. For every one of these, there is also if you look at like quick starts, for example, you can get a sense as to, and again, the quick starts in a lot of these cases are sort of goofy because, as I said before, they're all REST calls, right? So it's sort of like, how do you do a REST call in Node, right? So if you look, it does say things like, by the way, get an API account and, put your access key in and so on. So it's not as though there's no point to the sample, but the sample is mostly about, here's what the post payload needs to contain. And then obviously at the end, there's a very simple, in this particular case, make the request, right? But if you look at the C# example, it is literally almost the same. The difference being that, the manner in which you create the object that you then serialize to JSON to become the payload for the post is, a little bit different, right? But for every one of these APIs, there is a collection of documentation like this that covers everything from how to do it in your language of choice to a complete point by point by point reference doc for everyone. Any other questions? Yes, in the back. So the question is, for the facial recognition API, where is that data stored? So the way it works is so there are a couple of different answers to that question depending on how you solve this, right? There is a custom vision API separate from the face API. The face API is very much optimized around facial. So that data that you use to train it is ultimately not stored. So it's a little bit of a trick. The images you use to train it are actually not stored. The result of the training is stored, if that makes any sense, right? So if I took 10 copies of myself and used it to train the model, those copies actually, well, they do technically leave my machine to be part of the training input, right? But once the model is trained, the system doesn't persist those in the cloud, right? Those 10 photos really only exist on my system, right? It's the point being that it's not as though if I take 10 images of myself and I train the thing, it's not as though when I send it the 11th image and say, is this also Steve? It doesn't actually go back to the prior 10 images and say, does this 11th image look like the 10? What it's actually doing when you're training it, and it's more complicated than this, but conceptually what it's doing is it's taking the 10 images and saying, you've told me these are all photos of Steve. What do they all have in common, right? You're telling me they're all of the same thing, but they're obviously not the same photo. What aspects, what characteristics do they have in common? And then the training codifies that list of characteristics into a model. And then when I send it the 11th photo and say, is this Steve? What it's doing is analyzing the 11th image I've sent as a candidate to be me, and what it has deduced from having previously analyzed the 10 images of me that I gave it to train, and then saying, does this new image that might be Steve have enough of the characteristics that I was trained to say these characteristics mean Steve, right? For me to say I've got a high enough confidence this is Steve, right? And so if not a lot of those characteristics align, you might get a 0.02 confidence. If a lot of them do, you might get a 0.98, right? But it's not that the training data stays up in the cloud, right? You do transmit it for the actual training to occur, but that exists in memory and then is discarded. So there's no persistent store in Azure of my 10 photos in there. Does that make sense? Yep. Yes. Mm-hmm. Yes. So in this particular case, right, it is unsupervised learning. It's reinforcement learning, right? Because what I'm basically doing is I'm saying, here's 10 photos of Steve, right? And so for the record, right, part of the answer to the question is I'm oversimplifying, because in most of these services, right, it's actually not just one kind of algorithm or one kind of machine learning pattern or approach that's being used in order to get the answer. Part of the reason why the services are so valuable, because in most cases what they're doing is they're taking bits and parts of different algorithms that are all ingredients into the larger answer to the question, is this also a photo of Steve, right? So it is mostly reinforcement learning, because what I'm basically saying is, here's 10 photos of Steve, just do whatever you need to do to figure out that this is also a photo of Steve, right? I don't really care how you get there, right? Which is very different. It is generally reinforcement learning, but it's a little more complicated than that, right? Which is partly why, as a for instance, right? I mean, we talk about one of the interesting things when I start showing the face API is people often ask, like, is that how Windows Hello works, right? The answer is, well, kind of, but not really, right? Because think about it, Windows Hello is biometric authentication for your device based on your camera, right? But it's not just the visual camera, it's also the infrared camera, and that's what prevents you from fooling it with a picture, right? With the face API, it's just the image, right? There's no infrared camera for depth or anything like that. So you can absolutely fool this face API with a photo of me, right? It'll be sure it's me, right? Which again goes to that notion, right? If what you're building is a piece of software that's going to be security access for your high security lab environment, probably not a great tech for that. But if what you're doing is trying to say, let me build a photo sorting tool that allows me to say, here's the photos of, here's the folder of all the digital photos I ever took in my camera. Why don't you go pick out the ones I'm in, right? It works great for that, right? Because the consequence of a false positive or a false negative isn't a security breach, right? Which is why you need to always be thinking about, sort of the limitations of the technology. But again, it's that whole notion I keep coming back to of there's never just an answer. There's an answer with a confidence. And so you never ask the question without, it would be like me saying, is it raining out, right? Now I could say no, but I happen to know on my way in here it had started to sprinkle, right? So I'm not really 100% confident it's not raining right now. I'm maybe 92% confident, but it might well be raining, right? And so I can't just tell you the answer to that question. I need to also give you my confidence about it, because that allows you to make the right decision for your use case, right? If you're just saying, can I get to my car without getting wet, maybe I'll chance it because I don't have an umbrella. It's not a big deal if I get a little wet, right? But if it's instead like, should I go outside in my new silk shirt that's going to get destroyed if it even sprinkles, then maybe 92 confidence isn't, right? Anybody else? Oh, sure, that's fair too. Okay, great. So for the benefit of those in the audience, the question is, can you enhance or adjust the cognitive service if you needed to add something to it? The answer is, generally speaking, no. However, some services are designed with that in mind. So for example, the computer vision service has, like I was showing earlier, detect a bird, right? It works really good for things that the system has been trained to learn about, like, is that a bird, right? But imagine that you're Coca-Cola, as an example. What you really want to do is you want to find all the photos that have Coca-Cola cans in them. Right? Now, the problem with that is you can ask the general image algorithm, hey, show me all of those with cans. And you'll get, Sprite and Coke and Pepsi and A&W root beer and all kinds of other stuff, right? Because those all have cans in it. And that's a general enough question that a general algorithm can solve it. If you have a more specific use case where what you're trying to do is actually say, I want Coke cans but not Pepsi cans, right? Then there's something, for example, in the vision area called the custom vision service. Allows you to actually, in the same way I gave it a bunch of training data about photos of me, I could give it a bunch of training data about photos of specifically Coca-Cola cans. And then that custom vision service will become very good at detecting photos with Coca-Cola cans and not Pepsi cans and not Sprite cans and so on, right? So in general, a lot of the cognitive services are not designed so that you can sort of inject yourself into the algorithm with additional training data and all the rest of that. But some of them, however, are specifically designed expressly for that level of variability, because we know that the sort of more general purpose algorithm that just does like object type detection isn't going to be specific enough for your use case. And so in a lot of cases, some of the services are specifically designed around that. But as a general rule, the vast majority of the cognitive services are sort of, you use them out of the box and that's it. You get to additionally. Any other questions, online or otherwise? One, yep. So yeah, so that's a great question. So the question is, what do they cost, right? The answer is, the way it works is you provision them as part of your Azure service, right? So you go to the Azure portal and you say, I want a text analytics service. And it provisions one and it gives you an API key in exactly the same way, you would provision a Cosmos DB database, right? And you get a little keys thing and it shows you the API access key and so on. You provision a cognitive service in exactly the same way. The way these work is, and it's a great thing, I'm glad you asked the question because it's something I actually didn't touch on, right? I said you can experiment with them on the web using some of the web UI and so on. If you want to experiment with them in code, you can actually also do that. Almost all of the cognitive services they're all tiered, right? And so it's tiered based on number of API calls in a month or a week or whatever the duration is, right? I think it's monthly. But almost every one of them has a free tier, right? So for example, I think the sentiment analysis API, its free tier is like 10,000 calls a month, right? Which is totally enough for you to be prototyping and developing against and everything else. Probably not enough if you're going to have like more than 3 people use your service on a regular basis, right? But every one of these is provisioned through the Azure portal, and every one of them is subsequently is then subsequently on a tier, and everyone has a free tier so you can get started. So obviously, after experimenting on the website, the very next thing you would do, of course, is jump over to, now I want to write some code for real. How do I do that? provision the service in the portal, select the free tier to get started. That's more than enough for most of your development work. In fact, I've had lightweight production deployments that you do. And then after that, it goes up. It's like, whatever. And by the way, the answer might be 10,000 for the text analytics API. It might be 4,000 for another API. It might be 200 for yet another one, right? They're not all 10,000, but they're all sort of tiered in blocks of calls per month. And they're pennies. I mean, whatever it ends. They're not expensive, I guess, right? But their cost model is almost always per API call. That's how it's rated. Anyone else? Okay, we're done online and I'm out of time, so we're good. Thanks, everybody.